So we're very happy to have Professor Saurabh Kumar Singh here. He's a professor at the IIT Kanpur. He's one of the organizers of this great program. Thanks again. And he'll be talking about delta methods. Yeah. So please.
Thanks, Didier. So I am the last minute change. Munshi sir is supposed to come and give the lecture, but he could not come. So I am giving the lecture on his behalf. So there is so much talk about the dental symbol. So I'm not going to too much motivation and details. I'll just start. What is the delta symbol? Define function delta from set of integer to C with delta of n, taking value 1 if n is 0, and it is 0 otherwise. This is just delta symbol, and how we use this one. Suppose we have summation of the form, summation n of size n. This symbol I use often. This seems that n is varying over dyadic interval of the length 2n. Suppose we have two arithmetic functions an and bn. Both are the mysterious. They are oscillating functions. Suppose we know the individual value for an, we know the individual value for the bn, but once you multiply with them, we don't know anything. Suppose you have some another function cn, such that an times cn behaves nicely. That makes some sense. And similarly, bn times cn also behaves nicely. Then, yeah, you can take it bm times cm, they behave nicely. So you can separate these two oscillations using the delta symbol. So we write this sum as symbol as by using a w variable m, summation of n of size n, m of size n, an, bm. Now you have separated the two oscillations, but at the cost delta of n equal to m, delta of n minus m. Okay, now you have separated the two oscillations an and bm with the cost of some extra variable introducing m. Now you can expand this one using some your oscillations n of size n, summation f of size n, an, cn, and bm. We will see what are the cn's in for this course. And then these are the two separate terms, summation of n of size n, an, cn, and summation n of size n, bm. Now you can analyze these two terms separately and hope to you will get some non-trivial cancellations. So for this course, for this talk, we will try to expand this delta symbol, delta of n, because whole things boil down to get some nice expansion for this delta symbol. So first one, which we will be proved, is due to the Klusterman sum. It gives the expansion for delta n as 2 times real part of the integral 0 to 1, summation 1 less than c less than capital C. This one is bigger than a less than c plus capital C. There are two summations, a and c is 1. C is varying from 1 to some capital C. A is varying over residue classes modulo C, but A is coprime with C, 1 by AC. E of n a bar by C minus of nx by AC. So you have nice expansion for this delta symbol. So here you can take Tn's T of n. And second one is due to the Duke Philander and Ivanis. I will shorthand write DFI and Heath Brown. Which we have seen earlier in the talk for the winner is for that delta n you can expand as some constant CQ by Q square summation Q. This essentially runs from 1 to infinity summation of A modulo Q, but over the coprime residue classes E of NA by Q, H of Q by Q, N by Q square. Here H is some nice. Here also you can see that this weight function is like exponential of weight function. It's also a nice function. And this is also some nice functions. We will see the sub property of H and its derivative. We will see that H of xy is bounded by 1 by x and it's also derivative satisfied by some bound. We will prove the sub property for H. These are the two delta symbols which we will be deriving. Note that here we are using in the both symbol we are using the oscillations coming from the circle. Here we are using oscillation of the form E of y. As you know, this is denoted by e to the power 2 pi I times y, and they are points distributed on the unit circle. Okay, there are some other separate methods where we use oscillation coming from the this is you can consider this is oscillation coming from the GL1, and you can use oscillation coming from the GL2 form. It says that you can have expansion of delta symbol of the form. So this will be the third expansion, which will be proving, I think, at the end of third lecture. There are something mysterious objects called Fourier coefficients, lambda fm, lambda fn, bar. There is some weight functions, omega f inverse. If you sum over all f belongs to the Hecke basis, the level we will take 1. Then here you can get one expansion for delta nm plus 2 pi I to the power minus k summation c from 1 to infinity s of mnc by c, and then jk minus 1 4 pi square root of mn by c. Here you can see that you have also an expansion for delta symbol. All these harmonics, they are coming from the GL1, where S of M and C is the famous Klusterman sum, which is given by summation of alpha modulo C, varying over the coprime residue classes modulo C, E of M alpha plus N alpha bar by C. And jk minus 1 is the Bessel function of the order first kind. Okay, so we will see how they are derived. We will not go into the much application because Pessoa will talk about the application of delta symbol in the subconvexity problems, and Vinay is already talking the application of delta symbol for counting the rational points. It has some other application to other area of mathematics like shifted convolution sum problems and other. We will not go into much details what are the other application of the delta symbols. We will just try to prove some formulas. Okay, is it clear? So for the formulas, we will define what are the modular forms and what are the symbols appearing on the third formula. Okay, so as you have seen, and let us prove one of the Klusterman application of the circle method. like the expansion of delta symbol using the Klusterman sum. As we have seen in the first talk by the Balu sir, so nice, one of the simple formula for delta symbol, delta of n is nothing but integration 0 to 1 E of n alpha d alpha, as we have seen in the first lecture. And the classical version of a circle method start with take this interval 0 to 1. And as we have seen in the first lecture, the main contribution, suppose you have some function f of, suppose you have f of f, summation f of n, E of n alpha, then you can get the coefficient f of n by evaluating f of alpha from 0 to 1 against E of minus f n alpha, and then you derive this, divide this interval 0 to 1 into the measure R, which are concentrated about rational number with small denominators, A prime by Q prime and so on, and M is nothing but contribution of M, A Q, and small m was complement of measure R in 0 to 1. So we have seen that if you try to estimate the contribution for coming from the measure is minor R, this is called minor R, there are not much tools available. One can apply either Hua's lemma or you can apply the Wales bound. So what Klusterman did, he combined the measure arcs, he covered this whole interval 0 to 1 only with the measure arc. He disappeared minor arc. So what we do, Klusterman's idea, we write whole interval 0 to 1 as disjoint union of M, A, Q, where Q is parameter going up to some bit fixed Q and A is varying, and 0 less than A with A and Q is coprime. So what is this MAQ? This MAQ is different from the MAQ appearing in the first lecture. We will define what is this MAQ. For that we need Poiret fractions. Sometimes I always denote a number by A by Q, or sometimes I'll also change with A by C. Please be careful. Please be mindful. So we can use both notations, A by C and A by Q as a rational number. Okay, so Poiret fraction of order C. Let C bigger than equal to 1 be a real number. You can, if you want, you can take this one to be an integer. Then Poiret fractions of order C be denoted by f of C, each collection of all the rational points A by C such that 1 less than C less than equal to capital C, 0 less than A less than equal to C, but A is co-prime with C. That's all. So you have to include 0 because for C equal to 1, the 0 by 1 is also a fraction. So you have to include 0. So they are, how many they are? So for given C, A has 5 C many choices, and given, and C can range from 1 to capital C. So suppose we denote this one as some function f of C. So we have finite number of rational numbers, and we we put them on the interval, open interval 0 to 1. All of them are between 0 to 1 because A is less than C and A is strictly positive. So all of them are between 0 to 1. They are phi C in number. So we just put them in increasing order. 1 by capital C, 1 by capital C minus 1 and so on. Suppose you have two fractions, A prime by C prime. Here is A by C, A double prime by C double prime and so on. Suppose we have two consecutive fractions, they have some particular type of properties. I will just list them, we don't require, we cannot prove them. We don't need the proof. Suppose you have two consecutive fractions. A prime by C and A by C with fractions of order C with A prime by C is less than A by C, then they satisfy two particular type of property. Then first one is C plus C prime. This will be strictly bigger than C, capital C. And second one, their determinant is 1 in the sense that AC prime minus A prime C is 1. Yeah, so we will require these two properties for the Faraday fraction. And they are the proofs involve little bit geometry. There are many proofs given for this one. At least 3 proofs is given in the book of Hardy and Littlewood on analytic number theory. If you are interested to see the proof, you can refer to that book. But we will only require this property. Okay. Now we have open interval 0 to 1 and for fractions A prime by C prime, A by C and A double prime by C double prime. Then we define median of A. Median point, this point is A plus A prime divided by C plus C prime. And this median will be A plus A double prime divided by C plus C double prime. So exercise, you can take it. This A mid plus A prime and C plus C prime, they does not belong to HC. They are not Faraday fractions of order C. So their denominator will be always bigger than capital C. Okay. Now with these Faraday fractions, we define measure of or this Klusterman arc M A by C. Okay. Okay, one more property which we want, the distance of A by C with left product A plus A prime divided by C plus C prime. If you compute, this one will be 1 by C plus C prime. Yeah, just take the common ratio and use this property that AC prime minus A prime C is 1. And this one is A plus A double prime divided by C plus C double prime. This one with A by C will be 1 by C comma C double prime. So we define Faraday Klusterman fraction M AC is closed at the left median A plus A prime divided by C plus C prime and open at the right. A plus A double prime divided by C plus C. And this one is a by c minus 1 pi c, c plus c prime, comma, a by c, a by c plus 1 by c, c plus c. Note that from the constructions, the Fourier fractions, they are always disjoint. So you have disjoint union of MAC, which covers whole of 1. So we have closed interval 0 to 1. This one is given by disjoint union of 1 less than C going up to capital C. This capital C at your expense, you can choose depending on the problems. And this one is 0 less than A less than small c, but A is co-prime with C. And M of S. Now we want to derive the Crusterman version for the expansion for the delta symbols. Suppose f is periodic function. Suppose f is periodic function with period 1 satisfying some nice property, then you have you can write f of x is given by summation an of nx, and where you can get the coefficient am by integrating f of x over the parameter m of x. Now the zero Fourier coefficient is important, so we write a naught. We denote this one as mu of f. This one is nothing but integration 0 to 1 f of x. Okay. So we have integration for whole interval 0 to 1. Now we want to use the Fourier fractions so that we can write interval 0 to 1 as disjoint union of Fourier intervals M, A, C. So this thing is nothing but mu of f is nothing but summation 1 less than C going up to capital C, summation 0 less than A less than equal to C, but A is co-prime with C, integration over MAC. So this condition I just write as shorthand notation C less than equal to C, summation A modulo C star. This is the nice shorthand notation for this whole condition. And this one is integration MAC is nothing but A by C minus 1 upon C, C plus C prime to A by C plus 1 by C, C plus C double prime, f of x dx. Yeah. I have just write interval 0 to 1 in disjoint union of MAC, that's all. Now here I want to make this one to be independent, this integral to be independent of this numerator first. I will do the change of variable x going to A by C plus x. Dx into dx. So this mu f is nothing but the things remain same. C going up to C, summation of A modulo C star. Now this one integration, this one we go to minus 1 upon C, C plus C prime. I will break at the 0 plus integration of 0 to 1 upon C, C plus C double prime, f of just apply the change of variable, we will get f of a by c plus x. Now this is the property we will be using. Consider the first integral. Let me write it again. Summation 1 less than c going up to c, summation of a modulo c star integration of. Now I write 1 by c d f of x plus, for the second part, I also write this one as 0 to 1 by cd in this first integral where in first integral we write t plus c prime that is equal to d. Okay, t plus c prime I am writing as d. Now d is congruent to c prime. All this congruent I am writing modulo c, and c prime. From the first one, you can see that c prime is congruent to a bar. D is congruent to a bar mod c. So this one, from here, we get that a is congruent to d bar mod c. So you can write a as d bar and plus some integers ac. So a by c is d bar by c plus some integer k. So a by c plus x is d bar by c plus x plus some integer k. So now a by c, which is appearing in this first interval, since f is periodic with respect to the period 1, you can replace by this quantity. Yeah, since f is periodic with period 1, we have f of a by c plus x is nothing but f of d bar by c Okay, similarly, in the second interval, we are replacing t plus c double prime as equal to d. Now d is congruent to c double prime, and from the relations which I think I just erased, you can see that this is congruent to minus of a bar. So from here you can replace f of a by c plus x is nothing but f of minus of d bar by c. So from this, combine these two, you obtain mu of f as summation c going up to capital C, summation of a. Yeah, I will change it later. Now going up to d. Now this will be going up to d, but d is still is co-prime with c. We will see what is the range for d. Integration of 1 by cd to 0 f of d bar by c plus x plus integration of 0 1 by CD f of minus of d bar. Okay, now let us see what are the range for the D. Now D, which is nothing but C plus C prime. Using the first property of the fractions, this will be always bigger than capital C, because in first property, if you have two consecutive fractions, A prime by C prime and A by C, then sum of denominator is always bigger than your prescribed value capital C. So C plus C prime is always bigger than D. And since C prime for a fraction of order capital C, this will go up to C plus capital C. Okay. And since D is congruent to A bar and A is C is co-prime, or from here also you can see that D is co-prime with C. Its condition is on D is nothing but summation 1 less than C going up to capital C. Summation on D, D will be bigger than capital C. This will be less than C plus capital C. D is co-prime with C. Integration of 0 to 1, 1 by CD. Now change the variable x going to minus x there. F of d bar by x, d bar by C minus x plus f of minus of d bar by C plus x d of. So this hold for any periodic functions with period 1. Now again, I will apply the change of variable. Apply x going to x by CD. So this interval depends on this property. This depends on C and D. So to make independent of numerator and denominator, just apply this change of variables. We obtain mu of f as this one keep as it is. Summation 1 less than C going up to capital C. D is bigger than capital C, which is less than C plus capital C. D is co-prime with C. Now you get 1 by CD and integration part 0 to 1 f of d bar by C minus x plus f of minus of d bar by C minus x dx. So this expression holds for any periodic functions which is of period 1. Now if f is such that f of minus x is same as f bar of x, f of minus x is same as f bar x. So here you have the f plus f bar, that's give the 2 times real part of f. In that case, mu of f is nothing but summation 1 less than C going up to capital C, summation over D bigger than C less than C plus capital C. D is co-prime with 1, 1 by CD f of 2 times real part integration of 0 to 1 f of d bar by C minus of x. Okay, so f plus f bar is nothing but 2 plus your point of f. Now apply, take f of x. Then this side is nothing but mu f is nothing but delta of n, and right hand side is what you want. Summation over C and 1 for all these things. nx by cd. Okay. So this part, because all these things they are arithmetic objects. N is integer, D is an integer, C is an integer. They are called arithmetic. This part, since x can vary over the real number, this part is called analytic. So these oscillations of the form E of Na by C is called arithmetic oscillation. And oscillations which can have the points other than some rational points, they are called analytic oscillations. Okay. Now suppose you have some equation to detect and size of equation is of order n, as in the case of binary analytic part, this oscillate like E of minus of nx by cd. If you differentiate with respect to x, then what will be you will be getting n by cd, and then some E of all these things. And size for this differentiable, suppose this one is f of x, then fj of x is nothing but n by cd, the power j, and some exponential things. The derivative size okay. So C going up to C is of size capital C, and D is also of size vary from C to 2C, but as size it is also of size capital C. So C times D is also capital size T square, and N you are detecting equation of size N. So this one is nothing but N by C square to the power J. If you choose C square to be equal to N, if C square is equal to N, then there are no analytic oscillation. This is sometimes vaguely give some vague explanation why we choose C to be the square root for the size of the equation. So that we can kill the analytic oscillations. We can work only with the arithmetic oscillations. Do you have any questions so far? Yeah, no, from CD here it is CD. If you want to make from 0, you have replaced x by CD. That's all. Okay, it's there. Okay, one obstacle with the circle method. It's not really obstacle. Thing is that this analytic oscillation C is also involved. This arithmetic oscillation C involved with this analytic. So for that, to overcome this one, the Duke-Friedlander one is they derive the expansion for delta symbol, where A is totally independent of the analytic objects. So that is delta of n. So let me write it here only, so we can make expansion. This is So C and D, C is of size capital C, so this will be of size 1 by C square. So you can write 1 by C square summation C from 1 to infinity, summation of A modulo C star E of NA by C. Instead of A bar, you will get A, and H of U C by C N by C. Now this analytic function is totally independent of your A or A or D, what you have written is. So this analytic function is totally independent of A. So if you have some exponential sum and you want to evaluate explicitly this exponential sums, then this circle method is useful because this weight function is totally independent of A. But essentially both are the same. But you cannot argue that this circle method is better in comparison to this because both them essentially give the same strength bound. Yeah, so what is the time? Time? Okay. Yeah, so I think today we will cut short our lectures. We have already 2 loaded, so we have already conducted 3 and 4.5 hour lectures. There is another 1.5 lectures will be coming on. So I will stop for today. So we will meet here today at 6. And I will continue in the next lecture. I will continue Vinay has already derived this expansor for h of n. I will just quickly recall derivation, and I will derive some property of this weight functions h of xy. And in the last, we will derive the expansion for delta symbol using the GL2 harmonics.
Thank you, Saurabh.